Are we online? Good afternoon, everyone. All right. A few communications, if you're interested. So today is the midterm surveys due date. So Patrick and Thomas are not going to accept anything past today. Just email them. It's easier if you want. If you see them, you can hand them the piece of paper, but email is the best. Okay, so that's number one. Homework 2 is Monday. And since, as you may recall, I'm not here on Wednesday, I'm on travel, I think I'll give you 2 days. So you have Tuesday and Wednesday. We're not going to have class. It doesn't mean that it's harder than homework 1. It's probably easier than I don't know. That's my point of view, but you'll judge. But I'll give you 2 days. It's not a big deal. Now, after that, we have the test in new physics building room. I don't know. You have it on your, I'm sorry? 1001. I have it on my calendar. So don't come here. Okay? That is also ready. I'll tell you right away. It is designed to have even less calculations than last time, if you really stop and think about the question. So it shouldn't be that much difference. Still 10 questions. There is maybe 1 or 2 true or false. Very, very similar, but probably even less calculations, if you have been on track with everything that we talked about. Now, STK, I finally have a lot of people with a license. Almost everybody now has a license, almost. Still only one master's level certification. Quite a bit first level. Now, I have seen a couple of people in my office hours asking a few questions at the very beginning. I'm not surprised. STK, the way, at least when I did my certification, it was really designed to be user-friendly, so even non-engineers should be able to get certified. As a matter of fact, one lady from AGI, who is in the business department, who is not an engineer, came to visit us when I was at RPI, and she was STK certified. She said the way it's designed is not only for engineers in principle. Of course, you can use it a lot more than a non-engineer. You can do more stuff, but it shouldn't be a big deal. But again, the second level certification is not a one-day business. So if you're planning to do that, now it's the time. Okay. Any questions, concerns? I'm going to reproject probably the 3 plots we had last time, those delta V plots, just because maybe some of you still don't understand exactly what was going on. But let me finish this exercise here. Yeah, that's fine, you can stay there. So last time we said I'm coming in with an elliptical trajectory. This is my planet, the Earth. The ISS is on a circular orbit somewhere, right? And we were told that another spacecraft is coming from the moon, whatever it was before, on a hyperbolic orbit, and we are asked to compute, number one, the delta V required to go from, let's see, this was point B, this was point A, the 2 impulse delta V that allows you to leave the hyperbolic orbit. The velocity A was given as 10 kilometers per second. So you have to leave the hyperbolic path, go into an elliptical one, and reach B and apply another delta V. So as it usually happens, when I rush at the end, there are some imperfections. What was the imperfection in my drawing? It doesn't affect your calculations. It doesn't affect the numbers you get when you compute the delta V's, but the way I sketched the situation here was not correct. Has anyone noticed?
Are you talking about how the line goes through the orbit? How I think you called it 3, went through the orbit.
Right, I did something like this because and it doesn't even match my sketch here. Is that possible? Can you go on an ellipse like this? No, it's not possible. Why is it not possible? So if this is my apogee of the transfer ellipse, and this is my perigee of the transfer ellipse, why is this not possible? It is not possible, I'll tell you. It is not possible. They're not going to intersect here. These two orbits, the circular one and the transfer elliptical orbit, are only going to touch at this point, and they're going to be tangent, so the delta V is a pumping maneuver, as we called it. But so, if that's the case, so this is not possible, it should be something like this, right? Why is this second line okay? Well, yeah, it wasn't going to be tangent, but yeah, that is one reason. Can you give me another one? What is the definition of perigee? If this is the perigee of this ellipse here, is the closest point on that orbit, right, to F. Now, if the radius of perigee is equal to the radius of the circle, which is what I want, then any other point on that ellipse is at a higher distance from the focus. So there was no way that I can have this intersection here. So again, it doesn't really change the fact that you're going to compute the delta V's the same way we've done, but that is not possible. So this is not correct. This other one is, okay? So fix that in your notes. All right, so the question number one was compute the delta V, so it's two impulses, and then the other question was, what does this angle need to be? I think the position of ISS for some reason was called C as well, point C. So this angle is phi C to B. What does this angle need to be so that when the spacecraft that it's coming from far away reaches point B, the ISS is also there? So basically it's like asking you, when do I need to be here and start this trajectory so that I'm going to rendezvous with the ISS, right? So you have to time all this. And we said, well, the time I'm going to spend on, what do we call this? Let's try to be consistent. This was trajectory 1, I believe, and this, was this 2?
That was 3.
Okay. 3 and 2. So 3 is the transfer. So the time I spend on these 3, which is half of an elliptical orbit, has to be the same time that goes from C to B, and knowing the angular velocity on a circular orbit, I can figure out this angle. But let's do the delta V first. Let's do the delta V in A. So before the burn, I do know what my velocity is. It's given. So what I have to figure out is now the velocity on 3, right? So velocity A 3. How do we do this? And again, there were numbers given, of course. This distance was radius of the Earth plus, you know, let's just call these RB and RA. How about that? I don't really need to give you numbers. Then you can plug in the numbers. So this is RA, and this is RB, okay? Makes it easier. So how do you compute the velocity of the spacecraft at point A if it's on trajectory 3? What is the start equation? It's always the same. Yes?
Is that going to be square root mu over r?
Nope. I'm going on trajectory 3, which is an elliptical one. It's not a circle. It will be on the circle. Yeah. So if it's not a circle, unless you memorize more or less how it looks like after you solve it, what I suggest is you always start from this and go from there. It's really not that big of a deal. It's a two-step solution. So this is the generic energy equation, which translates for point A on trajectory 3 into minus mu over what is 2A is RA plus RB. And this is known, will be a numerical value. So this is going to be the velocity of point A on trajectory 3 squared over 2 minus mu over RA. Isn't this getting boring at this point? It's always the same stuff. Okay, so I'm not going to solve it. You solve it, and you get that VA3 is 5.1830 kilometers per second. So your first delta V is 10 minus that. Now is that, well, clearly it's slowing down. Why I'm asking the question. I'm going from 1 to 3, so it's clearly a retrofire. So it's 4.862 kilometers per second. I never write the signs here. You could write the sign. You can say that it's a minus just to remind you that it's slowing down. If you want, But again, if you compute a fuel consumption after that, the delta M, you want only magnitudes. That's all you care about. And I really am not going to do it because it's the same story. At point B, you apply the same expression. Here you have RB. Here you have velocity B on 3. And find velocity B on 3, which is what I have here. 8.4995 kilometers per second. Now velocity B on 2, which is the circular velocity, what one of your colleagues was suggesting is square root of mu over RB, sorry. And this is it more or less? It's less, going on a smaller orbit. I swapped the name of the orbits here, I'm confusing the numbers. Okay, 6129 kilometers per second. This is 6129. So the delta V in B, which is also a retrofire, you reduce the velocity, is the difference of those is 0.8866 kilometers per second. That's it. So that's how much it costs you in terms of delta mass. So the total delta V, of course, is the summation of these two, okay? And if you really want to do it, it's 5.7486 kilometers per second. Remember, everything that is above 1, it's a big deal. It's taking a lot of your mass. And in fact, if you do the math with the delta M formula, this means 85% of the mass. So you come in with a ton spacecraft, and you do these two maneuvers, and you have 250 kilograms left. 150 have gone in space. Yeah. Yes?
So you can basically like only do one or two maneuvers?
Yeah, big. Yeah.
Like ever?
Well, big maneuvers that require big changes of orbit like this. You're coming from far away on an hyperbolic one, and you have to slow down and then go into a circular orbit. This is a big deal. It's a big change. Yeah, they require pretty much everything you have.
One and done?
Yeah. I mean, geostationary satellites, when we put them into orbit and they have those 2-stage or 3-stage rockets, most of what goes up comes down. Now, SpaceX is landing those rockets, which is great. But usually the most of the mass would just be tanks for fuel. And the actual spacecraft that goes up, it's a little fraction of the initial vehicle mass, yeah. Yep. So you have to carefully plan these things. That's why Patrick is working on using solar sails and alternative means to propel spacecraft, but those are very tiny forces, so it takes forever. There was a question at some point, someone raised his hand.
I was just asking what the VB2 value was.
7.6129, if I've copied it right. Yeah, 6129. Now the other question was, what is that angle? And we said that the period, if I am on trajectory 3, the period of 3 is given, well, period of an orbit is given by this expression, right? In this case, is the same major axis of 3. So if you substitute here, what is A of 3? It's RA plus RB over 2, right? So with the numbers I gave you, again, I'm giving you the final numbers, but just recall that RB was, the height of this point was 500 kilometers, while the height of this point was 5,000. So with those numerical values, you get that, of course I called them the other way, okay. The period of 3 is, I think I gave you this last time, 8,679.1 seconds. That's your elliptical orbit. You're running only half of that, right? So we're going to use T3 over 2 at some point. While the orbit that is the circular one, the period of that one with the same exact formula, except A is now RB, not A. It's 5,676.8 seconds. And we said, okay, now what do I do with this piece of information? Well, I know that the ISS is on a circle, so I can talk about a constant angular velocity, right? And so my angular velocity of the ISS, or if you want on orbit 2, it doesn't matter, it's the same thing, is 2 pi over the period, right? Okay? And so to compute that angle that I want, phi CB, is the angle covered by the ISS, which is moving at this angular velocity in what amount of time? T3 over 2. Make sense? So the question, if you just open the book, it's in your book, this is a problem from your book. The question is, what does this angle need to be when I start this maneuver here, the first burn? So basically, during this time, from A to B that I'm transferring, the ISS has to cover this angle to be here. And so the phi from C to B, well, it's going to be this, omega, ISS. I don't think I have the number for that one, sorry. T3 over 2, right? It's a product. And if you do it in degrees, I have a 275.2 degrees. That's it. Questions, concerns, issues? We need to move on to something new now. So this is what you do. We analyze specific types of maneuvers, Hohmann transfer, what we had done last time. Now today I'm going to do the bi-elliptical case where you have 3 burns now. And the idea of adding burns is usually the same. You want to save fuel if you can. But you can do maneuvers from all sorts of orbits, from a hyperbolic one to an elliptical one to a circular one to a parabolic one, as long as you do the same at the junction point. Compute the velocities and figure out what the difference has to be. And so far, they've been all aligned. So I come here, and this is the perigee of the hyperbolic orbit. So I'm coming in with 10 kilometers per second, and I decide that I have to slow it down to whatever BA on 3 was, 5.1 or 2. So I have to reduce this, but it's in the same direction. So my delta V is against the initial velocity, right? But they're all parallel to each other. So that's what we've done so far. We're going to start seeing cases where you need to add a vector that is not parallel to the original one. Any questions? Concerns? No? Okay. Do you want me to pull up again that plot from last time? Those 3 plots? And go over them again? It's fine. We can do that. No? Okay. So we'll do bi-elliptical transfers now, which goes back to the original situation when we have 2 circles and we did the Hohmann transfer. I'm going to start with 2 circles, and the transfer from the small one to the big one, again, you can reverse easily, is done with 3 burns. There are 2 ellipses involved. Okay, here it is. Let's see if we can make it understandable. F is here. Your circle, inner circle is this one, for example. Your bigger circle will never look like a circle, but it's supposed to be this one. And we call, so this is the planet, point A, point, I'll explain why these are called A, B, D, D. Okay? So what you would do before, what we've done before, is going with the Hohmann transfer from A, for example, 1 burn there, 1 burn here, and I'm done, right? So this is the Hohmann transfer. Well, there is a way to save fuel and go to a little bigger ellipse, go past the radius of the bigger circle. So with the apogee, you go past this point D, and we call this point B. I apply another burn here that goes outside with another ellipse of the bigger circle, and then my third burn is down here, and I'm calling this point C. Do you see that? So this is my Hohmann transfer here. What we have done already. You can do many different things to end up in the big circle. This is 3 impulses. You go away from the circle on this ellipse, which has a point B, which I decide now. We're going to play with this and see if it's convenient or not to do it. And then from B, I do another burn. I go on an even bigger ellipse and close it at C, where I correct and end up on my trajectory that is the desired one. So let's call the starting circle 1. This is H, the Hohmann transfer. The first ellipse, I'll call it 2. The second one, I'll call it 3. And the goal trajectory, my big circle, is 4. And I think we can give names to a few radiuses here. We have to. Okay, let's see. This is RA. Of course, this is RC. And then we have RB, this point down here, right? Sketch is understandable? RA, RC, RB. Okay. Well, it's the same story. We compute the delta V's and compare. And there is another plot similar to the ones I showed you last time, but this is only one that compares the two. So when do you do the bi-elliptical? Of course, when the total delta V is less. But it's not always the case. It depends on this point. Ideally, if you move this point to infinity, that drives down your delta V. But just the fact that I've added now another ellipse, I pay it in what? What is the cost of doing this? Say that it's reducing my delta V. That's great. But what is the downside? Time. It takes a lot longer to do this. So it has to be convenient. Okay, so what I'll show you, I'm not going to go through the entire calculation, and I was almost thinking about giving you this as an uncollected homework to complete it, because your book gives you some formulas, the total delta V for Hohmann and the total delta V for the bi-elliptical. It just gives you the final expressions without demonstrating those. It's really not that difficult, but so we can start, and then you guys finish it if we don't have enough time. So what they do is, first of all, this. We're going to compute the delta V Hohmann and the delta V bi-elliptical normalized by the velocity on the circle, which is my starting circle, V, I call it VA or V1. Well, that's trajectory 1. V1, which is square root of mu over RA. And also what they do, distances, all those distances that you see there are normalized by RA. So in other words, since what I start from is a given, it's a circle of radius RA, and once you give me RA, also the velocity is given, they just compute a-dimensional delta V's. So the formulas that I'll show you, they basically give you delta V Hohmann divided by V1 and delta V bi-elliptical divided by B1, and then they compare the two. But it's, it's really not that big of a deal, but that's what they do in the book. And everywhere where you see an RB and an RC, they're going to be divided by RA. And so you will see parameters in there that are alpha, which is basically RC divided by RA. And there is a beta that appears in these expressions that is RB divided by RA. It's just the way they are presented to you. It's commonly done that way. Okay, so let's start. So basically what we'll do today is we give the final expression for the delta V for the case of Hohmann and for the case of the bielliptical, which is really just a function of alpha and beta and the initial circle. So you can basically use those expressions every time you need to do one of the two maneuvers. So let's start with Hohmann. And as I said, if we don't have time, you guys can finish because the procedure is always the same. Okay, what do? I start with the first impulse, right? So I'm doing Hohmann now. Minus mu over. Am I missing something? No, I'm not missing anything. What is the same major axis of that H trajectory? RA plus RC. Make sense? Even though I have RC on this side, remember the outside is a circle, so it's RC also on this side. Right? So R, already forgot, what is it? RA plus RC. Guess what? Velocity. It's a lot of bookkeeping, I agree, and it's very boring, I agree, but if you don't do it this way, chances are that you're going to miss a piece and your delta V is not going to make any sense. Divided by RA. Okay, so that is the velocity. Well, this is on H. If I am on what did I call that? 1, of course, is that. Square root of mu over RA. So my first delta V let's see. Do you have any questions? If it's not clear, I can go over it again.
I don't understand how you got the RA plus RC.
Oh, so should write what I'm doing here. This is velocity. Well, this is what I'm computing, right? It's the velocity on point A if I'm already on the transfer orbit. On this one here, right? The Hohmann one. You see that? So this distance F to A is RA. This distance F to D, it's RC. I have it between F and C, but that's the outside trajectory is a circle. So this is the same major axis. From D to A is the same major axis of this transfer ellipse, the Hohmann one. Okay? And so my velocity there is, let's see, it's square root mu over RA times square root of 2 RC over RA plus RC. If you solve that. And I have collected this mu over RA. So in other words, my VH, AH is, since I want to normalize with that, what I call V1, is V1, how do I make those RC and RA disappear? I want to make alpha and beta appear. Beta for now is out of the picture. I'm not doing the bielliptical, but divide by RC, numerator and denominator here, right? Agree? What happens if I divide above by RC? That's what is left. And what I have down here is 1 plus, 2 alpha. I divide by RA. I'm normalizing by RA. Dividing by RA, this is what I get, and here I have 1 plus alpha, right? I haven't chosen to do this. This is what is done in textbooks. This is how you have to look at those final results they give you in those plots, because it's usually normalized quantities. That's what they do. Okay, make sense? Okay, and so your first delta V, of course, is going to be normalized. The delta V in A for Hohmann divided by V1 is going to be equal to, I'm going to accelerate, right? I'm going from this to this.
same thing as VA1?
Yeah, it is. Yeah. Agree? Disagree? Okay. Well, you keep doing this. Can we erase something? Probably here. So remember, we normalize by the velocity on the circular orbit and divide everything. All the radiuses that you see, you divide them by RA. So you don't see any radiuses flying around anymore. What happens in D? So I want to compute the velocity D on the Hohmann transfer. How do I do it? Same story. Minus mu over RA plus RC is equal to velocity dH squared over 2 minus mu. Now I am at RC. And so keep going with this. Yep. Well, you do it, what is it? What is that? Is 4. That's my final orbit, right? On 4, I have what? What do I have on 4? I'm still doing the Hohmann one. It's a circle, right? So velocity d4, I'm not even going to do that. It's square root of mu over RC. Okay. So VDH, do I have it here? I should have it here. Yeah. Okay, let me see if I have space. Yeah. VDH, if you solve, is square root 2 mu RA RC RA plus RC. Do we all know what I'm doing when I go from this to this? I'm solving for the velocity. That's all I'm doing, okay? Yes?
Is that a minus 1 next to the expression that you have for delta VAH over V1?
Yeah. Yeah, because the delta VAH is what? Is this velocity that I want on the Hohmann transfer minus this velocity which I had on the circle. So it's this divided by V1, which is what is left here, minus V1, which divided by itself, it's a 1. Yep. Okay, so remember I want to normalize, so let's do it with this. And I'm really going to stop doing all these calculations because it's over and over again. If you go to the bielliptical, you just have to do it one more time here. How do we normalize this one? Divide by RA numerator. This is what I have. Do it here. I have an alpha, right? RA plus RC. Is that clear? Okay. But remember that all the velocities will have to be divided by V1. So I want to bring out a square root of mu over RA from this thing. I want to collect it in front of it somehow. So square root of 2 over mu, it's fine. 2 mu is fine. How do you bring out the 1 over RA? Bring out the 1 over RA, right? That's all you do. So mu over RA multiplies 1 over alpha 1 plus alpha. And this is V1 again. Yes? Am I missing an alpha here? No. So this is not normalized at all, right? This is what you get straight from the energy equation. You want me to do it? The VDH? I'm solving for this velocity from here. You do the common denominator, this is what you get. Subtract, bring this on the other side, and this is what you get, okay? Then I say, since the solutions to compare the plot that I'll show you now, to compare the bielliptical and the Hohmann, they're all as a function of delta V's normalized by the circular velocity of the initial orbit and you don't see radiuses appearing anymore, you only see their ratios appearing, alpha and beta, and alpha is RC over RA. I'm going to manipulate this to make it look like what you will see. So the square root of 2 mu, okay, it's fine, I just brought it outside. Then I take this fraction, divide top and bottom by RA. I have a 1 left, I divide by RA, this RC over RA becomes an alpha, and then I still have an RA plus RC here. I don't like those. But since I am going to also normalize by the circular velocity, which is mu over RA, I'm going to take out of this square root a term which is 1 over RA, which is basically like dividing by RA the denominator, again, okay? So I make this thing appear in front, and it's like dividing this part by RA, which gives me 1 plus alpha. Algebra, a lot of it. And this is only the Hohmann one. So if you guys are fine with this, I'm going to stop and show you what you get in general, basically for these two expressions. The delta V, as I said, on the Hohmann transfer divided by V1, which is a function, a first function of what? Of alpha only. And then the delta V on the bielliptical divided by V1 will be a second function of alpha and beta. So this only depends on the ratio between RC and RA, and that makes sense. I only go directly from the small circle to the big circle. There's nothing else. So the delta V due to the Hohmann transfer, whatever the final expression is going to be, cannot depend on anything else than alpha. Remember, alpha is RC over RA. Desired circle, starting circle. Beta is RB over RA. Now I'm introducing this RB because I want to use an additional ellipse, and I'm going outside first and then I come back. Okay? So the second one, the bielliptical, the 3 impulse maneuver, is going to be a function of alpha and beta, because I choose beta. I choose RB. Okay? So let's see how they look like. So I hope the procedure is clear. You compute the delta V at each point, you get whatever you get, make it such that the radiuses disappear, divide numerator and denominator by RA until all the radiuses are gone, divide by V1, which is square root of mu over R, and you're going to get the following expressions. So I have them here, the steps. I really suggest that you guys, because they don't solve them for you in the book, you go spend half an hour, because really it's not going to take more than that probably, on a piece of paper showing to you that these are the things that you get. And then if you want, I can scan my note and post them. It's really not a big deal. But it's a good exercise because you're computing impulses without having actual numbers. You just have R, A, B, and C. Okay. So this is exactly what they do. They say, I'm going to know what they call it V0 or VO. That's my V1. So all the delta V's, what they call delta V bar H and delta V bielliptical bar, they are the delta V normalized by that. So they are adimensional delta V's, okay? Because again, your initial circle is a given. So you can normalize everything by the parameters that describe their initial trajectory. And those are its radius, which also sets its velocity, because it's a circle. And then, as we said, alpha is the ratio of RC over RA, and beta is RB over RA. And those are your final formulas. So if you want, because you're tired of doing all these energy balances at each point, someone is asking you, compute the delta V on a Hohmann transfer that goes from a certain RA to a certain RC, compute this, input there, multiply what you get by V0, and that's your delta V. Make sense? Okay. Bielliptical, someone tells you, I want to go again from RA to RC, but I'm doing it bielliptical with a bielliptical transfer, so I have an RB here that is given. Well, compute beta, go to this other formula. It's going to take a few more steps to compute this. Whatever you get is the normalized delta V. Compute that, multiply times V0, and that's your delta V bielliptical. So those are the final solutions. So you can just go to those every time you hear Hohmann bielliptical, if you want. Or you can do the delta V's one at a time at each point. I don't see why you should do that, but some people have fun with calculations, right? So now, if you take those, the point is, why am I doing this? I am doing it hoping that the second one is going to cost me less than the Hohmann one, even though it takes more time because I'm running on 2 ellipses now. It may cost me less. Yeah, I know this plot is probably much nicer than my drawing on the board, but okay, this is what you get. I don't know if I can make it bigger than this. Nope. Can I? Zoom. Yeah, I can zoom. Look at that. All right, so this has to be read more or less like we did last time. On the x-axis, you have basically the goal where I want to be divided by the initial circular trajectory. So this is what you want to do in case you're going for a bigger circle. Again, everything is reversible if you go into a smaller circle. And on this axis instead, you have, in case you do a bi-elliptical transfer, the ratio of RB over RA. How far you want to go outside of that big circle with this point here. These are all pumping maneuvers. There's no change in direction of velocity. It's only increasing or decreasing. Okay, this line is where RB and RC are the same. Now, if RB and RC are the same, what am I doing? I'm doing a Hohmann transfer, right? So the bi-elliptical collapses into a Hohmann transfer. And then the way you read this is the following. There is an asymptote here at 11.94 for the ratio between RC and RA, where below that, forget about bi-elliptical, you do Hohmann, because it costs less. So someone has gone through the pain of computing a bunch of different values for alpha and beta, computing the corresponding delta v's and creating those plots once and for all. So again, it's like a lookup table. Someone tells you, for this situation, what is it best, to do a Hohmann transfer or a bi-elliptical? Go here, and you're done. You just look at this table. You just locate where you are, okay? So if I'm giving you, I don't know, 7, I want to make my radius of RC 7 times bigger than RA, Hohmann, done. Don't even think about bi-elliptical. Then this is an asymptote. So up to this point below this line, Hohmann here is still more efficient. But after this line, past that point, is bi-elliptical. Okay? And that's pretty much it. Any questions? Yes? No, there's a question there.
What happens below the RB equals RC?
What happens between RB, yeah. What is physically happening here? What do you think? You're going in, right? And then you do this, right? And so is that, which one is more efficient? They don't tell you there. I believe I don't know why it's missing that information, but I believe the Hohmann one is always more efficient, if I'm not mistaken. No, it's the bi-elliptical. Yeah, it's the plane of the bi-elliptical. So I think that this is really what you have. From this line on is bi-elliptical, but except this area here. So in this area is Hohmann, and here is bi-elliptical. Below that, I'm just thinking if it's physically meaningful to do that. Let's see. Let's think about this. Yes?
That just be the big circle if RB and RC equals each other.
Well, when they equal each other, that's fine. I'm doing a Hohmann. But can I do something like this? Can I really do something like this?
I mean, you can, but when you're at that
Mm-hmm.
burning an apoapsis, so it's really not worth it to make a burn there.
Well, I'm just, geometrically speaking, I think I'll have to think about this. I don't know, the point is, I don't know if you can geometrically do it in 3 burns. That, I guess, my main question. I'll have to think about this. Yes?
So what's stopping, these are points that you're choosing arbitrarily? Right?
Yes. Yes.
So what would be theoretically the most efficient point? Period.
If we look at that plot, the most efficient point is, Well, they don't show you the values of delta V, right, in that plot. They don't. There is not such an information there. But if you actually go to those formulas that I give you and you try to play with numbers, here they are. If you start moving this point B far away, it usually brings down your delta. That's what it does. It brings down your delta V because the maneuver you do there is very weak. That is the idea.
So making that B really, really large is actually the most efficient.
Yeah, but the time goes to infinity. Yeah. So that's a good question. I have to think what happens below that line. I think there is nothing below the line because I don't know if you're really doing anything that can be either 2 impulse or 3 impulse. That is, I think, the point. Below the line, so that is the limit for the bielliptical. Because if you do RB equal to RC, you're doing Hohmann again, right? So below that, let me think about this and I'll get back to you guys. Because I think there is a reason why there is nothing there. That's probably, you can't, I'll have to think about definitions of perigee and apogee. I don't think you can make it in 3 impulses, the way we're thinking about it. So, but I'll double check. Any other questions? So we've done 2 and 3 impulses so far, nothing more than that. No other questions? I think we can stop here for today. Thanks.